Hello, my name is Stephanie Buchan, and thank you for tuning into the Hamamatsu Photonics channel. Today, we're joining in the global celebration of Earth Day, and in honor of Earth Day, we are kicking off our newest series of shows discussing how photonic solutions can be utilized to overcome both short and long-term environmental issues. To start things off, we thought who better to co-host today's show other than our in-house expert, Masakazu Katsumata.
Hello, glad to see you in Earth Day. My name is Masakazu Katsumata. I'm in charge to research photonic solutions on environmental issues. Recent years, I'm working for application of photosynthesis and biotechnology that for environmental protection and agriculture. That is green science. Now, the green science is one of key technology for carbon net zero and sustainable society.
Thanks for joining me, Katsumata-san.
You are welcome and thank you for having me.
So, in the past decade or so, I would say the world has become very acquainted with the term climate change. In your research, what have you found to be a driving factor for growing issues surrounding climate change?
So our planet had recently seen significant population growth, and according to the 2011 Organization for Economic Cooperation and Development, OECD for short, the world population is expected to reach 9 billion within the next 30 years.
For reference, the world population in 2020 was approximately 7.8 billion. So, in less than half a century, we could see human society grow by a number roughly equivalent to the population of China. And that must be great for the economy, but I imagine would come with even more demand for energy and other resources.
Yes, exactly. According to the OECD report, the world economy is projected to grow up to 4 times in size. As a result, the world will see growth in man-made source of pollution. These include increasing amount of sewage, waste, unrecycled plastics, and higher emission of greenhouse gases or GHGs.
That spells a recipe for loss in biodiversity, safe water for drinking and agriculture, food and livestock, and more. And as you and I have discussed about before, on top of the challenges for life both on land and in oceans caused by the lack of clean water, the world over will find increasingly erratic weather patterns.
Yes, we have seen after hurricane or tsunami, these weather patterns not only have economic cost but also put human life at serious risk.
Exactly. So, why don't we try to address the question at the heart of these environmental challenges? What is the main source of climate change?
When we think about the main source of climate change, we must think about pollution.
Right. And we can break down pollution into three categories: emission of greenhouse gases or GHGs, plastic pollution, and water pollution.
Starting with the emission of GHGs or greenhouse gases, this is driven by the need for energy. With a growing population and economy, this need for energy becomes even greater.
That's very true. Globally, people rely on energy for electricity, heat, and transportation, with around 80% of energy today still coming from fossil fuels. So, what's the issue behind burning fossil fuels for energy?
Where once fossil fuels are burned, they are not returned. This is unsustainable by nature. Also, by burning fossil fuels, massive amount of carbon dioxide or CO2 and other GHGs are emitted.
hmm Yeah, our World in Data Global stated that fossil fuel-based CO2 emissions increased from 20 gigatons in 1990 to 36.4 gigatons in 2021. So, for those who aren't familiar with this scale, 16.4 gigatons is equivalent to roughly 3,280,000,000 elephants. And as more of the CO2 and other GHGs are emitted, more are trapped within the atmosphere, increasing the average global temperature.
As a result, average global temperature has climbed around 1 degree Celsius within the last 100 years. The OECD also predicted average global temperature to grow up around 1.5 to 2.5 degrees Celsius in the next 30 years.
An immediate and severe effect of higher average global temperatures is higher ocean temperatures. According to IPCC SR 1.5, ocean warming could wipe out 70 to 90% of coral reefs if average global temperatures reach 1.5 degrees Celsius.
While 1.5 degrees Celsius may not sound like much, the steady increase in global temperature has already resulted in higher sea levels and extreme weather conditions, which, in addition to harming life, causes economic strain.
Mm. And over the last 30 years, over 11,000 weather disasters, climate, and water-related hazards have taken the lives of 2.06 million people across the globe and have resulted in economic losses upwards of 3.64 trillion US dollars. Unfortunately, it isn't only ocean warming that we need to be concerned about when it comes to burning fossil fuels, right, Katsumata-san?
That's correct. As more CO2 is emitted from burning fossil fuels, more is absorbed by the oceans. The more CO2 is absorbed by bodies of seawater, the lower the pH.
And the lower the pH, the more acidic things become. The acidification of oceans is destructive to marine ecosystems because it makes it more difficult for ocean life to build shells and bones through calcification.
Yes, the calcification process is vital to many types of marine life, including already at-risk corals.
So, as a result of both ocean warming and acidification, researchers have found that roughly 2.8 million acres, equal to over 2 million American football fields, of coral reefs are lost every year.
And with the loss of the coral reefs brings the loss of a variety of aquatic life that depended on them.
Exactly. And life above land depends on these coral reefs as well, with around 70% of oxygen in our atmosphere coming from the ocean.
We can see how much of the environment is at risk as a result of GHG emissions.
Yes, we can. However, it isn't only GHG emissions that we need to work to resolve. Plastic pollution is another major source of human-induced climate change. And this may not be a surprise to our listeners, as plastic is everywhere and in everything, from electronics to construction materials to clothing. The list goes on.
And the amount of plastic that is produced keeps growing to match the demand of growing population. The United Nations Environment Programs, or UNEP for short, recorded a soar in plastic pollution from 2 million to 348 million tons in the last 60 years.
This 174-fold increase is expected to keep increasing, with UNEP projecting the global plastic industry, valued at 522 billion US dollars, to double in capacity by 2040. This skyrocket in plastic production has correspondingly brought about a boom in the volume of plastic pollution covering the planet.
And with poor recycling and waste management, the amount of plastics ending up in the oceans has boomed as well.
Between 4 and 12 million metric tons are littering the oceans every year, and this number is expected to triple within the next 20 years. But it doesn't stop there. Once these plastics are in the ocean, they are broken down in the environment until they become microplastics. So Katsumata-san, what is the danger of having microplastics in our oceans?
Well, most importantly, although there is a large number of microplastics in oceans, we have very small amount of knowledge of the risk on the ecosystem and human health. There are many hypotheses. If we follow the food chain, we see possibilities that microplastic pose a risk to human health. Marine life that ingest microplastic may be eaten by humans. So some of the microplastic contain various chemicals that were used as additives. Some of the additives are suggested to adverse influence on ecosystem.
Studies are ongoing and so far have shown that ingesting microplastics can potentially affect hormonal, metabolic, and neurological activity. So you might be thinking, if disposing of plastic or trying to recycle it isn't effective, can we just burn it? To which the answer would be no.
I agree. Open burning of plastic adds to air pollution. A better way to manage plastic pollution is creating technology that can sort and recycle plastic waste.
Exactly. And we will talk more on that soon. But before that, let's jump into our last source of human-induced climate change, water pollution. Now, the previous two topics both delved into the impacts of the other types of pollution on water quality and marine life. So, how do we set water pollution apart?
Well, we can look at water pollution from the view of wastewater and runoff water. Wastewater is a byproduct in many processes within human society, agriculture, industry, daily life, and so on. When we look at wastewater from agriculture, there are pollutants from fertilizer, pesticide, and animal waste. Once these pollutants wash out the body of water, eutrophication may begin.
Mhm. And eutrophication consists of two phenomena. One is the growth of harmful algal blooms, or HUB, and hypoxia. Just as these fertilizers were once used to promote growth of vegetation on land, so too will marine ecosystems consisting of algae, phytoplankton, and seaweed grow quickly. When this happens, this is known as an algal bloom. But what's so bad about marine ecosystems flourishing, you might ask? Well, although the aquatic plant thrives quickly, it does so at a cost to its own survival and its neighbor's survival.
Exactly. The harmful algal blooms or HAB can produce dangerous toxins that can sicken or kill people and animals. And when the algal bloom die, soon after hypoxia begins.
Hypoxia refers to a low presence of oxygen, and because aquatic life relies on oxygen to exist, without it, these areas become known as dead zones.
Unfortunately, the dead zone can also come from urban wastewater runoff and industrial spills. These situations also put human health in danger by contaminating drinking water.
Exactly. It's essential that processes for effectively separating clean drinking water from contaminated waters or wastewater be thoroughly studied and implemented. In 2015 alone, unsafe drinking water resulted in the loss of 1.8 million lives, with roughly 1 billion people made ill from exposure.
Add to the fact that 2.3 billion people live under water-stressed conditions, and we see a need for sustainable water management and monitoring. Which brings us to next point. How we can we begin to address these problems? How can we manage greenhouse gas emissions, plastic pollution, and water pollution?
Thanks for sticking with us. To bring us back to Katsumata-san's question, there are two routes we can take. One is preservation of the environment, and the other is reduction of pollution. Now, these are just a few examples, but bear in mind that there are limitless use cases for photonics within this arena. Let's start with monitoring GHGs, or greenhouse gases. Some examples of these gases are carbon dioxide and methane. These can originate from automobiles and industrial settings like factories. Now, these gases and many others can be absorbed by light of various wavelengths, from ultraviolet or UV to the mid-infrared or MIR.
Right. Wavelength depends on application, but one example is using a quantum cascade laser or QCL paired with a mid-infrared or MIR detector. The QCL is unique for ultra-narrow line widths. This gives users very selective and sensitive measurements. The detector in this example could be an indium arsenic antimonide or INASP detector.
Mhm. And for shorter wavelengths than the MIR, one can look to light sources like an LED, which is useful for cost but limited to individual gases based on the wavelength emitted, or a xenon flash lamp, which offers you high brightness and broad range of output wavelengths, which allows you to detect multiple gases. On the detector side, one can consider silicon photodiodes as a cost-effective option, or cooled near-infrared or NIR photomultiplier tubes, PMTs, for high sensitivity measurements.
Exactly. Normally, we recommend selecting the right light source and detector for the gas or gases of interest. By making the right selection, analysis with fast response, high accuracy, and long life can be realized.
Yes, and the same can be said for the potential in creating a solution for plastic pollution. One example uses both X-rays and light in the near infrared or NIR range for plastic sorting. And as we mentioned before, plastics typically contain additives that were introduced during the manufacturing stage. One additive that is typically monitored for is a brominated flame retardant. But before the non-flame retardant plastics can be sorted from the flame retardant plastics, wastes must be sorted in general.
This is done by using a dual X-ray line scan camera to remove glass, metal fragments, and other non-plastic materials. After plastic is isolated by various photonic processes, it can be sorted into various types of plastic according to their characteristic wavelengths using indium gallium arsenide or InGaAs uh, area image sensors.
Mhm. And these area image sensors can be used within a camera or a spectrometer optical configuration. We've seen spectrometers using interferometer designs, such as our Fourier transform near-infrared spectrometer or FTNIR engine, to detect such additives. In any case, the most common cutoffs on the long wavelength cutoff side for sensing in this application are 1.9, 2.1, and 2.5 microns. Furthermore, metal fragments can also be recycled using a technique called LIBS, or laser-induced breakdown spectroscopy, which uses a pulsed solid-state laser as the light source and a mini spectrometer as the detector. Using this technique, one can differentiate types of aluminum by comparing spectral data between high-purity aluminum and duralumin.
And the water monitoring side, we see a range of applications sensing pollutants that causes eutrophication from domestic and agricultural wastewater. But before we monitor these pollutants, it is necessary to have qualitative measurement to identify which contaminants exist within wastewater.
Mhm. Yeah, and on the identification side, one may consider a mini spectrometer as a detector for its ability to capture multiple wavelengths simultaneously, and pair this with a xenon flash lamp, which benefits from the high peak intensity that one can use to overview a various set of components within a sample. Now, these components may be contaminants or nutrients depending on the application.
Some contaminants monitored in wastewater are nitrate and nitrite. These cause eutrophication and lead in dead zones. Many types of water contaminants have light absorbance or fluorescence. That is useful to detect and identify the contaminants. For nitrate and nitrate, absorption can be found in UV range.
Another application, precision agriculture, may be monitoring for nitrogen compounds and carbohydrates. Whatever the application, however, once the component or components of interest have been identified, the next step is monitoring their concentration.
To do so, one can consider LEDs or xenon flash lamp as a light source. On the detector side, multi-pixel photon counter or MPPCs and hot multiplier to PMTs give sensitive measurement of typical fluorescence.
Mhm. These detectors can detect even weak signals from low concentrations of algae. The goal of such measurements would be to halt any early signs of eutrophication by preventing, predicting, and tracking these low concentrations. We can also look at eutrophication prevention from the perspective of soil analysis.
That's right. Monitoring soil contents can be effective in reducing water pollution caused by agricultural runoff. One example of this application is drone photography using visible to near-infrared light. It can assess fertilizer concentration and others throughout the field.
Mhm. This can be accomplished using near-infrared hyperspectral imaging, which utilizes our long wavelength type indium gallium arsenide, or InGaAs for short, image sensors. And then, once the field has been analyzed from above, spot samples can be collected for further measurement. One can consider using the Fourier transform near-infrared, or FTNIR engine, for its detection sensitivity up to 2.5 micron.
Now, there are many techniques to consider when investigating solutions to human-induced climate change.
And what we've discussed today is just scraping the surface of what is possible within the world of photonics.
So at Hamamatsu, we will continue to support our customers' goals of creating systems for on-site, real-time measurement for conditions from industrial setting to out in the field.
And with applications focused on monitoring gas emissions, plastic pollution, water quality, or soil content, our goal remains to help customers develop these systems, which can benefit from our high sensitivity detectors and high power broadband light sources. We're also keeping a finger on the pulse for future innovations with collaborators on technologies for optimizing photosynthesis in both land and aquatic ecosystems.
Yes, my own research has found that photonics applications on gases, plastics, water, and soil quality are useful to support optimizing photosynthesis and other bioprocesses to enabling a bioeconomy. The bioeconomy uses renewable biological processes to produce biofuels, bioplastics, and food. And it is necessary to reduce CO2 and sustainable water management. The photonics we discussed today are useful to monitoring not only environmental issues, but also this bioprocess.
So just as Katsumata-san continues his research, we hope that through Hamamatsu's expertise in optical sources and detectors, and by sharing our global network of collaborators excelling in analytical technologies, that we can strengthen the scientific community's advancements in designing and producing the next generation of photonic systems for resolving our ongoing climate changes. That's it for today, but check our channel for upcoming podcasts within this new series.
We will have speakers discuss topics such as what we spoke about today in detail and tech, how photonics technology can help.
And as Katsumata-san had introduced earlier, we will be doing a unique session on photonics and the development of a bioeconomy. But for now, thank you again for joining us today.
We hope to see you next time.